My name is Kisei. I am a marine biologist at PIFSC, for those who don't know me. I study mostly where species are and how species responds to the environment. And today, I'm here to talk about heat. I'm here to talk about specifically extreme heat, specifically in the ocean, and specifically in an area just outside of Pacific Islands in these regions. And specifically, I talk about more like historical context. So things I'm going to talk about today has already happened. Okay, not a future, happened. So I'd just like to thank for my collaborator, Hannah and Daisy. And let's begin by where we are today. So 2024, 10 months ago, many of us were fairly alarmed how this, at the global scale, we saw one of the largest jump in SST on geological histories, right? It was largely driven by Atlantic, but also in Pacific, inside this rectangle, we saw this huge jump in SST. That's how we started 2024. Right? So this is not just a one-time incident. If you look at this historical trend, what you notice is that you're seeing a unidirectional shift in the temperature across these regions, right? So you notice that years, way back in years, you're seeing more colder, more recent years, you're stacking on top of it. So temperature is getting warmer at the surface levels in the Pacific Oceans, right? So 2024, 2023 was not just a one-time incident, but it's just the results of this system shifting from cold to the warm state. So if you just look at this in more like a statistical schematics, right, you're seeing like a shift in the bell curve from colder side to warmer side. So most of the people tends to think like, oh yeah, average temperature increases, right? But more and more of us are looking into more of this tail end of this bell curve. So as the bell curve shifts to the right, what used to be rare, extreme heat event, becomes more of a common phenomenon. Right? So this has been studied fairly for quite some time on land. Paper from 10 years ago showing these extreme summer heat days across Europe as exponentially increased in recent years. If I remember, just in the Pacific, it got narrower, actually, so the temperature variability has actually shrinked. But not by, not much details, but within that red rectangle, we were seeing a slight contraction in the size of variabilities. Okay, thank you. Hopefully this time. This is where I left off? Yep. Okay, so yes, shift in bell curve, right? More, what used to be extreme event becomes more like a normalized event. In the marine system, Hobday 2016 came up with this beautiful statistical definition of how should we define this marine heat event, right? So you have a baseline. And then you have what we call like a threshold, like a 90 percentile. Any heat signals goes above this threshold for 5 consecutive days, we count as a marine heat wave. So this has become a very common definition of what count as extreme heat event in the marine system. So NOAA has been deploying, producing this global scale marine heat event visualization using high resolution SST product. But Ryan gave a great talk, touched on this subject. So what's high resolution at the global scale may not be high resolution enough at the regional scales, right? Especially in our regions, we study areas around islands. And these are characterized by very complex coastlines. So you need to have a resolution that's high enough to resolve these geographical features, right? So this is where these high resolution SST product comes in. So it does fairly much better job resolving like islands, right? So I'm going to talk about more about this high resolution SST analysis. So inspired by this Hobday definition of marine heat wave, I decided to look into the change in the frequency of marine heat event just outside of Pacific Islands using this high resolution SST product. Right? So this is a kind of tedious process. Every single grid cells, you can define the threshold, right? First, you can define your own baselines. I decided like the first 30 years of this data sets, and you basically can determine where this, if you have a 30-year baseline, what is the probability of once every 30-year type of event, right? So in the statistical definition, that is 96.7 percentile. If you have a 50-year baseline, that's 98th percentile, right? If you have a 10-year baseline, that's 90 percentile. So it's up to you. But in this case, I decided that 30-year baseline, 96.7 percentile, and simply count number of instances when SST goes above or stay below this threshold, and calculate it individually for every single grid cells around every islands in the Pacific regions. So the idea is that you're turning this SST product into more like a binary layers, right? 0 or 1s. It's gridded, so you can simply calculate this number of cells that spiked above this threshold. And you can either calculate the fractions, right, by either area or annual, right? So this is just a simple definition of, quantifying a change in frequency of marine heat event, right? It's not the severity or it's not the magnitude, it's a change in frequency of extreme marine heat event. So now you can visualize this change in frequency of extreme marine heat event around islands in this Pacific regions. So we name it, we published a paper 2 years ago, we named it Local Extreme Heat Index, right? It's an annual fraction of monthly SSTs exceeding localized threshold, in this case, in 96.7 percentile, right? Based on your own baselines. In this case, 1985, 2014, 30-year baselines. What you're seeing is that in these like west side of Big Island, over the last decade, these locations seen extreme SSTs in over 30% of months every year, right? Statistically, these events should happen only once every 30 years. Now happening 30% of every year, from 2015 to 2023, right? You can also look at the seasonal differences, right? Is it happening more in the summer, or is it happening more in the winter? In this case, you can see this, the southeast side of Big Island. You can see like largely the change in frequency of heat event was happening during summer months. You can look at other regions. It's a global. You can look at anywhere, anytime. Somewhere way down in the southwest, Mariana Islands, you can see how this decadal evolutions of a change in frequency of heat event. Right? So this is the Mariana Islands. You can just look at Guam. This is the way it kind of gets a little difficult to see. Guam is a slightly smaller islands. But this high-resolution SST does its great job looking at which side of islands has seen more increase in frequency of heat event, especially during this month of January and March. So now you can look at this regional divergence in the frequency of heat event. You can simply stack them together, right? We have about 40, 50 islands in the Pacific, and you can see how which island has kind of like shifted out of its historical bounds, or which island has remained steady in terms of change in frequency of heat event. You can also look at time series of areal fractions. Just to see how this change in frequency has increased over time. Interestingly, at July 2019, across these 47 islands that I studied, roughly 80% of coastal waters were clocking in at the SST values above threshold. Technically, this event should happen every 30 years, once every 30 years. You can also look at the regional differences. I forgot to put a label here, but what you're seeing is the northwestern Hawaiian Islands, the peak came in after 2019, but the Samoa says the peak were largely aligned with 2019 timing. Another question that we could study is that, so I have an index of quantifying a change in frequency of heat event, but some of my co-authors and I are discussing, are there any correlations or lags by comparing this index to more conventional marine heat indices like reaching alert or degree heating weeks, right? So there are many ways to do this, but more simply that we can just simply run cross-correlational analysis. The way I set up this analysis is that if the bars stacks on your left side, my index leads those other indices, right? If the bars stuck on your right side, these conventional heat indices lead my index. So that's just a way of looking at it. Is are there any statistically significant correlations, or are there any lags between these two indices? But interestingly, that my index, which quantifies the change in frequency of heat event, tends to lead other marine heat indices by maybe 5 or 6 years. This was still a pattern after we detrend both time series. So there's some indication that this index, if you start picking up the change in frequency of heat event, a couple years down the later, then you start seeing a change, increase in degree heating weeks or bleaching alert. I'm sorry, I forgot to put this first. Again, same patterns, right? My index lead that degree heating weeks by maybe 5 or 6 years across the Pacific regions. Same patterns remains after we detrend, right? So there's some indication that there is potential lags, right? That holds across the spatial domains between these two heat index. So takeaways. Last decade, 2015, 2023, almost 25% of US Pacific Islands waters clocked in with extreme heat event. Or event previously expected only once every 30 years. This was happening every year, roughly a quarter of islands last decade. Right? We really saw just a jump in the frequency of these marine heat events across Pacific Islands over the just last decades. Really just last 9 years, we saw a little jump in these frequencies. Another thing is that change in the frequency of extreme heat event often precedes other marine heat indices, such as bleaching alert or degree heating weeks. So maybe if we look into deeper, maybe we can have some sort of like a forecasting mechanisms between these two indices. So I'll end here. Thank you.